A lamp, also known as bulb, converts electricity into visible light. There are several ways to do that, including incandescent, discharge, and solid-state lamps. Here, we'll review a few types that are commonly used in buildings. When solids are heated, they emit visible radiation at temperatures above 1000 K. In incandescent lamps, this solid material is tungsten, the filament. Incandescent lamps are the least energy efficient type of electric lighting and tend to have a short life. However, they possess several key advantages. They're inexpensive, dimmable, available in many sizes and shapes, and attractive for its warm light and excellent color rendition. As a special type of incandescent light, halogen lamps, also known as tungsten halogen, consists of a tungsten filament sealed into a compact transparent envelope filled with halogen gas. Halogen lamps have a longer operating life, higher luminous efficiency, and higher color temperature than incandescent lamps. A variety of shapes are available with halogen lamps due to their small size, such as MR as well as the standard A shape. Discharge is a type of lamp that passes electric current through a gas to activate its atoms and molecules to emit light. As the most common discharge lamp, fluorescent lights are filled with mercury vapor gas. When an electric current energizes the gas, they produce ultraviolet light that is invisible to human eyes. The UV light then causes the coating on the inside of the tube, phosphors, to glow and emit visible light. Fluorescent lamps can be in linear, circular, and U-bend shapes, and the diameter of the tube can be in T12, T8, or T5. The smaller the diameter, the higher the efficacy. To energize the gas when starting, extra voltage is needed, and it requires a device called ballast, which also maintains a lower operating voltage when the lamp is on. Compact fluorescent lamp is a newer type of fluorescent lamp in which the fluorescent tube is twisted into a shape similar to an incandescent bulb, with the ballast contained in a cup at the base of the bulb assembly. Metal halide lamps combine mercury and metal halide under a high pressure, which produces both ultraviolet and visible light. A special glass bulb filters the UV component out and only emits visible light. It is commonly used as light sources for sport fields, parking lots, street lighting, and indoor high ceiling lighting for retail stores and factories. They emit a strong white light and have a long life and high luminous efficacy. LED lights involve passing a current through a two-lead semiconductor to produce light. When the voltage is applied to the leads, electrons' negative charge from the N node combine with the electron hole's positive charge from the P node, releasing energy in the form of photons at the PN junction. LED chips produce violet and blue light. Phosphor is applied on top of the chips to absorb the energy of violet and blue light and transform it into visible light. Two major advantages of LED lights include energy efficiency. LED bulbs do not generate nearly as much heat as incandescent bulbs for producing the same amount of light. Long life. LED lights can last up to 50,000 hours, while incandescent bulbs burn out after 1,000 to 2,000 hours, and CFLs after around 15,000 hours. LED lights can also be dimmable and good for color rendering. Each glass light bulb is designated with the shape name indicated by a letter. Some lamps have an internal reflector with reflecting coating. They can therefore provide directional light. The shape of the light beam is cone-like, pointing to a direction rather than sending light to all directions. The cone of light is in a range of beam spreads from narrow spot to white flood. Color rendering index measures the ability of a light source to reveal the colors of objects in contrast to a natural light source. It uses a scale from 0 to 100. The higher the CRI, the better the color rendering ability. These graphs shows the spectrum distribution of common lamps and their approximate CRI. Daylight has a CRI of 100. Incandescent light with a CRI of 95 is a great light source in terms of color rendering. This particular cool white LED light has a CRI of 80, whereas the clear mercury light only has a CRI of 17, indicating it is far from a full spectrum light. A luminaire is an electrical device that contains the lamps. A luminaire can send the light generated by the lamps in various directions. A candle power distribution curve represents the variation in luminous intensity in candela in the vertical plane passing through the light's center. The curve is obtained by taking measurement at various angles starting from the straight down direction. Usually, two lines are present in the chart, a solid line and a dashed line. These lines indicate the light distribution and intensity from two orientations through the center of the light fixture, the transverse and axial planes of the luminaire. This is a 2x4 12-er fixture with two tube lamps. For example, in the transverse direction, the fixture provides about 300 candela in direction pointing directly downward, and about 200 candela in the direction 60 degrees off the downward direction. Candle power distribution curves are used to indicate where a light fixture sends its light, upward, downward, or both. An upward, indirect light can provide a softer ambient glow through a secondary reflection by the ceiling, while a downward, direct light provides a direct illumination for the workplane. There are multiple light distribution patterns in between the direct and indirect lights for various applications. Not all light produced by a lamp will exit the luminaire. Some will remain trapped inside and dissipate as heat. Fixture efficiency is the amount of light in lumens leaving a fixture divided by the total amount of light generated by the light source within the fixture. The luminaire's physical characteristics affect how much light can exit and be directed at the workplane. Ballast factor is a number between 0.7 and 1.2. It is to account for the impact of the ballast on the lighting output of a fixture. Luminaire efficacy describes the efficacy of the entire luminaire, including the lamp, ballast, and luminaire efficiency. The luminaire efficacy rating LER is a metric for comparing the energy efficiency of different fixtures. Lighting power density is the amount of power used by lighting per unit of building area, measured in watts per square foot. The LPD standards of common space types in this table are selected from the 2015 version of the International Energy Conservation Code. Here, we will use a day-bright fixture as an example to illustrate how lighting metrics and data are displayed. The fixture cut sheet offers useful information such as spacing to mounting height ratio for performing preliminary fixture layout. Mounting height MH is defined as the distance from the fixture to task plane, which is usually 2.5 feet from the floor. Assuming the ceiling height is 8.5 feet above the floor in this office example, the mounting height will be 8.5 minus 2.5 equals to 6 feet. Therefore, the fixture spacing S will be equal to the mounting height times 1.6, which is equal to 9.6 feet. If the fixtures are to be placed in a 2x2 ceiling grate, The actual spacing, which needs to be an increment of 2 feet, can be 8 feet on center. It also provides various energy performance data as discussed earlier, such as the ballast factor, the input wattage, and lumens per lamp, which is 2,850 lumens per lamp for this fixture. Based on this, the total lamp lumens can be calculated as 2,850 times 3, since there are 3 lamps in this fixture. The cut sheet contains other data such as coefficients of utilization that are needed for lighting calculation. Coefficient of utilization evaluates how efficient light is delivered in a given environment. This value shows the portion of light produced by the lamps that reaches the work plane considering various light loss factors. The CU value for fixtures is determined by the room cavity ratio and the reflectance of the interior surfaces. General lighting provides a space with overall ambient illumination. The most common type of fixture for providing general lighting is troffer mounted on ceiling grids. A troffer is a rectangular or square light fixture that fits in a modular lay-in ceiling grid. There are 3 common troffer lights: prismatic, parabolic, and the newer volumetric. The prismatic lens is designed to diffuse the light from the lamps and provide an even light distribution in every direction to minimize glare. These fixtures can emit a small amount of light above 60 degrees to illuminate the upper portion of the walls so that the cavity effect can be largely eliminated. However, they are often inefficient in sending light downward on the work plane. The reflective louvers on parabolic troffers are carefully designed to direct most of the light output downward towards the working plane, allowing the desired luminance to be achieved with a lower total lumen output. However, since parabolic fixtures direct the majority of the light downward, there's little or no output above 60 degrees. This can result in a dark ceiling and upper walls, the cave effect. Volumetric troffers have a photometric distribution that includes a fair amount of light in the 60 to 90 degree zone, tapering off as the angle gets closer to 90 degrees. It provides a better balance of luminance throughout the view field, and the space feels brighter, larger, and more open. Another approach to general lighting besides troffer is to use pendant fixtures that are suspended from the ceiling. They distribute light mainly upward to the ceiling, which in turn diffuses and casts the light back down towards the task. Pendant fixtures often provide both direct and indirect lighting to minimize glare on computer screens and create a soft, inviting, and even light environment for occupants. In spaces where flexibility is important, uniform lighting is crucial. Indirect lighting reduces luminous contrast and shadowing and provides a smoother transition between fixtures. It also has the potential to reduce energy use. Recessed lights, also known as can lights, are installed inside a ceiling or wall. They're typically comprised of 3 components: housing, trim, and bulb. A simple rule of thumb to determine the spacing of recessed lights for general lighting, such as for a kitchen, is to divide the height of the ceiling by 2. If a room has an 8-foot ceiling, recessed lights should be placed approximately 4 feet apart. If the ceiling is 10 feet, which is the case in this example, the spacing should be about 5 feet. To provide lighting for wall-mounted art and photos, use the 30-degree angle rule to place the light as shown in this diagram. A rule of thumb to determine the spacing of a row of recessed lights for wall washing is to simply place them with 3 feet in between and about 2 to 3 feet away from the wall. A more detailed method is shown in this diagram. Cove lighting is a form of indirect lighting that directs light up towards the ceiling or down adjacent walls from a cove to provide diffuse illumination to the space. Cove lighting fixtures are typically mounted on a wall or located within a ceiling coffer. This type of indoor lighting hides the fixture and can create a decorative effect. The configuration and dimensional recommendations are shown in this sketch. Cove fixtures need to be at least 18 inches from ceiling to create a smooth washing effect. Different configurations can produce different cove styles. In the center of the ceiling integrated with the ceiling coffers, wall washing coves, curved or round coves, etc. To determine the luminaire quantity and design a luminaire layout that best meet the illuminance and uniformity requirements, two tasks are generally needed. The first is to predict average illuminance levels, usually for ambient general lighting. One of the methods is the zonal cavity method, which is a complex and lengthy process, so we will not discuss in detail here. The second task is to predict illuminance levels at a given point, usually for task lighting, and this is based on the inverse square law of illuminance. If parallel surfaces cut a pyramid at different distances from the peak, the areas of those surfaces are proportional to the square of the distances. Because illuminance on a surface is determined by the luminous flux falling on the surface and the area, the formula does not change. The amount of light that falls on one unit of the area of these surfaces, which is illuminance, is inversely proportional to the square of the distance from the light source. This relationship is referred to as the inverse square law. Illuminance varies in inverse proportion to the square of the distance between the receiving surface and the light source. A lighting control system operates on an input-output process. The basic input methods are manual or automatic, and the basic outputs are dimming or switching. Manual controls require human to turn the lights on and off by using a switch and/or adjust light output up and down by using a dimmer. Automatic controls involve other devices, such as a computer-based building automation system, occupancy sensor, or photosensor, which automatically produce signals based on schedule, occupancy, or daylight level. Automatic control is much more effective than manual control in saving energy because it does not require human attendance. On-off switching is the most basic form of lighting control. Lights are either 100% on or 100% off. A simple switch integrated with a vacancy sensor can be an effective and inexpensive way to reduce energy use with on-off switching. A variation of switching is step switching, either bi-level or multi-level. For example, a two-lamp fluorescent luminaire may have two ballasts, each controlling a lamp, resulting in a series of stepped output levels. Output of 0%, both lamps off, 50%, one lamp on, or 100%, both lamps on. Step switching is a simple, relatively inexpensive method in buildings where sudden changes in light level will not be disruptive. Continuous dimming regulates light output with smooth transitions, providing good flexibility and precision to satisfy the lighting needs. It is desirable to spaces where smooth light level transitions are required, such as in offices, classrooms, design studios, etc. Continuous dimming is a great candidate to work with daylight harvesting. Open-loop daylight harvesting systems only measure the incoming daylight. The photosensor can be mounted outside the building or inside near a window. If dimming is used, the sensor measures the incoming daylight and signals the controllers to proportionally dim the lights based on the incoming daylight contribution. An open-loop system can control multiple zones from a single photosensor. Therefore, open-loop systems are generally economical for controlling larger areas with multiple zones in dimming applications. such as an open office. Closed-loop daylight harvesting systems measure the sum of the contributions from both daylight and electric light sources directly at the work surface, then adjust lighting output to maintain the illumination needed for the task. The closed-loop systems see the results directly and make adjustment based on the feedback, which makes this a closed loop. The primary advantage of the closed-loop system is that they measure the actual light level at the task surface. Therefore, they are able to make a correct judgment even if users close the blinds or take other unpredictable actions. Closed-loop systems can be expensive if they are serving a multi-zone space because each zone will require a sensor system. Therefore, they are generally economical for smaller spaces such as private offices.